All right. Hello, everyone. First response grades are posted. They matched like expected. Most people's grades, I think increased. Like more people increased than decreased, but there was some amount of both. But pretty much people's grades did not change significantly, which makes sense with the free response is only 20%. But from what I saw, the percentages kind of matched up. If people got around to 60% of the free response, they got around to 60% of the multiple choice, and so on and so forth. But yeah, if you want to come see them, they're in my office. It's pretty quick for me to pull it out for you and show you and all that stuff. I've had a few people come by already and all that good jazz. So, yeah, that stuff exists. We finished energy, so you all have your quiz on energy. That's this Saturday. That's due this Saturday. Hopefully you started practicing the problems on energy and all that. The quiz next Saturday is also kind of mostly energy, but with I think one or two questions on momentum. And then the quiz after that will be momentum, and the quiz after that will be fluids. So yeah, reminder to you all, the test 2 is going to be energy, momentum, and fluids. Energy and momentum are the two most important kind of pieces of it. Fluids is then also there. So I've kind of committed to that now. One of the things that's kind of tricky for some reason is finding practice MCAT exams. I have no idea. They're all behind paywalls for some reason. It was also really disappointing to figure out that the place where you get the most problems from is the people that do the exam, but also again you have to buy books and things like that. It's stupid. It felt like a cash grab, but that's whatever. I just saw that today. Anywho, someone sent me though a thing, and fluids is a decent chunk of things, and so I'm glad we are covering it. So maybe in future semesters I'll make it a bigger deal and more on the test. But currently the emphasis is going to be energy, momentum, and then some amount of fluids. But none of the free responses will be on fluids. But maybe a third-ish of the multiple choice will be fluids. So that's kind of the thing. Still will be significant, but yeah, you won't have a free response. All right, so momentum. This PowerPoint is very, there's only 2 equations in the entire PowerPoint. I say 2 equations. 2 new equations, and then there's conservation momentum and all that jazz. Momentum's great. Momentum, super, super, super useful as far as physics, engineering stuff is concerned. It's in a lot of ways, it's just another representation of Newton's third law. For every force, there's an equal and opposite force. I'll kind of show that as time goes on. But yeah, we'll define momentum. I'll give you all, your all's current understanding of momentum is probably very close to what I need you to understand conceptually about momentum. And I'll give you an equation for it. It's going to be the easiest equation in the entire class. It's as easy as an equation can get. Then we're going to talk about impulse, and then we're going to talk about conservation momentum, which is where the interesting stuff, that's the more involved problems and things like that. So, unfortunately, momentum is a vector. It matters. Momentum has velocity in it, and it matters which way you're going. So, you're going to have to split things into X and Y components. Just, be ready for that when we do stuff. So, you'll see that later on. Yeah, and don't forget kinematics. That's still bread and butter. But, so, energy, didn't care about XY. Now we do again. And when we get to fluids, then we won't care about it again. Those will be scalars. All right, so, again, you're all as intuitive. I have taught you nothing about momentum, and I can almost guarantee that most of you will get this question right. Which of the following has the most momentum? A football player running, a parked car, a baseball getting tossed to you, or a car going 10 meters per second? Give it a guess. There is only one right answer here. And something that might be helpful is converting that 10 meters per second to miles per hour. Is that fast? Is that slow? May or may not matter. All right, we'll go like 10 more seconds. Just give it a guess. All right, in 5, 4, 3, 2, 1. All right, so momentum is one of those things. So when I asked around people in my class this morning, what was satisfying was that two different people, when I said explain it, and normally I'd ask you all this question for the sake of time, I won't, but if you had to explain momentum to an elementary school kid, what would you kind of say? People thought about it. And two different people gave basically the same response, which was how hard it is to stop something. And that is actually a pretty good definition, in my opinion. It's not scientific by any means. You're not going to find that like online anywhere. But it gives you a good sense of momentum, honestly. And it works. So basically, let's use that application here. If that's kind of our everyday understanding of things that have a lot of momentum, they're hard to stop. A football player running, you might have a hard time stopping them, but you're going to slow them down a decent amount. Maybe you could stop them if you like grab their foot or something. I don't know. A parked car, you don't really have to work hard to stop. It's already stopped. It's very easy to stop a parked car. It's done. A baseball getting tossed to you, I don't care how fast that baseball is, you will stop the baseball. It might hurt you, but even if like a professional pitcher throws it at you, you're going to stop it. It's just going to hurt. A car going 10 meters per second. So reminder to you all that the really, really helpful benchmark, you do not need to have this memorized. I'm never going to test you on it. But that 27 meters per second is 60 miles per hour. I just find that really, really useful as far as checking, because I don't have any sense. If someone told me 5 meters per second, I have no idea how fast that is. I kind of go to this reference and I compare it to that. So 10 meters per second is like a third of 27, roughly. So about a third of 60 is like 20 miles per hour. You will not stop a 20 mile per hour car. Like it's not going to happen. If you step in front of a 20 mile per hour car, it will hit you and then it will keep going. You might slow it down a couple miles per hour, but not much. So, which is the most momentum? The car. 10 meters per second, 20 miles per hour. That's no one's going to stop that. It's not going to go well for you. And look, most of y'all answered that. You realize that's the hardest one. Whatever definition in your head you might have had for momentum, it seemed to work here. If you look up the definition of momentum online, what you're going to find is measurement of mass in motion, mass times velocity. Momentum is just generally defined as the equation, but my hand-wavy definition is how hard it is to stop something. Gives you a good sense of it. Lots of momentum, hard to stop. But yeah, easiest equation is mass times velocity. That's how you calculate something momentum. More mass, more momentum. More velocity, more momentum. And again, you all kind of have an intuitive understanding of that based on how it's used by people in various contexts. The symbol for it is P. If you all had a choice, what symbol would you prefer it to be? What would be better than P for momentum? If someone said, hey, I want you to write a shorthand of momentum, you get a single letter, what letter would you choose? M. Yeah, M's just already taken is the problem. M is taken by mass. Capital M is like a bunch of mass, so we can't use that either. So if you're like, why isn't it M? It's taken. You got to use a different letter. And we tried looking it up this morning, and there was like impetuous, but that doesn't start with a P either. And someone else found another Latin word, and that one started with a P, but I don't know. Whatever the reason might be, the symbol for momentum is P. Whether you like it or not, it is what it is. The units, if you're like, man, those units look weird, kilograms, meters per second, it's really easy to prove. What's the unit for mass? Kilogram. What's the unit for velocity? It just comes from multiplying them together. Again, momentum is not necessarily, it's not something you can necessarily see. It's not something, you're always going to calculate momentum. You can't just look at it's mass times velocity. You're always going to calculate it, so the units just kind of reflect that. The units are just, hey, multiply these two things, and boom, you got it. It's the same it is a vector, so it has the same direction as v, because mass doesn't have a vector, but great. Momentum, easy. We're going to use this a bunch. It is a super, super useful thing because it's conserved. As long as no external forces are acting on a system. If you add up all the momentums of everything in the beginning of something, and then you add up all the momentums afterwards, they equal. And it's super, super handy. And we're going to do some problems with that, where you can find out things that seem really, that you would not be able to do by any other means. There's problems I'm going to give you that you literally cannot solve without this. An example of that is you can have an asteroid explode into like 10 different bits that fly all over the place. And if you find the momentum that it begins with, which let's just say the asteroid's not moving, it's 0. And then you add up all the momentums of all 10 pieces, they'll all add up to be 0. It doesn't matter how it exploded. It doesn't matter how long it took to explode. It doesn't matter any of that. It turns out, though, if you add up all the momentums of the pieces, it equals what you start with. And it's just kind of a like crazy thing that you don't even care it exploded. But all right, great. This is a freebie. You can do this. I mean, you can do it in your head. No problem with using a calculator, though. What's the momentum of a 0.5 kilogram baseball traveling at 10 meters per second? Is it 12.5 joules, 5 kilograms times meters per second, 5 joules, or 20 kilograms times meters divided by second? Go like 10, 15 more seconds. Feel free to talk to each other. This class has gotten like quieter and quieter as the semester goes on. I don't know why. The first class, everyone was it was great. It was during these times people were like chatting, and then it's just gotten so quiet. It feels like the library. Like anytime I give you all something to think about or do, please talk to the people around you. I encourage you to. All right, you got 5, 4, 3, 2, 1. All right, so that's mass, that's velocity. It's m times v. It's 0.5 times 10, which is going to be 5, and the units are kilograms. And I'm going to write this a little different. Kilograms, meters per second. It's the exact same thing. Just showing you the same thing. Yay! Great. You just multiply them together. Super easy. It's fantastic. All right. I already mentioned this. What's the point? Momentum is conserved. I already said this a few times. What you start with is what you end with, and this is true even if the energy is not conserved, which is nice. So again, like you can have a situation where something literally explodes into a bajillion pieces. Energy is not conserved there because the thing might start with 0 energy, and then you have chemical energy, convert it, whatever. You can still do momentum with it. And yeah, the only time you can't use momentum if there's something outside the system speeding it up or slowing it down. So like if gravity is affecting the objects, then you can't quite use conservation momentum. So every single momentum problem we're going to do will basically be like on flat ground / gravity. It won't be going up or down and things like that because gravity does kind of ruin it all. You can still do it with gravity, but we're not going to do problems like that. All right. Collisions are exactly what you want them to be. There are two things hitting each other. Anytime, why am I mentioning collisions? If there's a collision, you're using momentum. If two things bounce off each other, or they start together and they break apart, or they start separating, they hit each other. If you have either multiple objects colliding or one object splitting, momentum. Guaranteed. Like, how do you know when to use a momentum problem? It's one of the easiest cases to identify if something splits into a bunch of pieces or things bounce off each other or like run into each other. You're going to use momentum. Rule of thumb. Always going to do it. Okay. I have this derivation written on this next slide, all pretty like. Here it is. But I'm going to quickly just like walk you all through this. So Newton's second law, we're going to express in terms of momentum. Why? Because it's just another way of looking at things. All right, F equals ma. Hopefully we're all cool with that. Hopefully we're like, yep, great, fantastic. Then what I'm going to do is say F equals the definition of A, which is the change in velocity over the change in time. That's like, what is acceleration? It's how much my velocity changes with time. Swap that in there. Fantastic. Okay. So what? Now I'm going to write momentum. Momentum equals m times v. Okay. So what? Now what I'm going to do is I'm going to get the change of momentum. And that's going to equal the change of m times v. And again, you all don't need to know this derivation. This is just to show you that the equation I'm going to show you in a couple slides didn't come out of thin air. All right, fantastic. Now, we're not going to do any problems where mass is going to change. We're not going to have any problems where like you lose mass somehow, some way. So we're going to say mass doesn't change, but my velocity can. Okay, so we pull out the mass. And then the last thing we're going to do is we're just going to divide both sides by change in time. You're allowed to, whatever you do to one side, you can do to the other. It's like multiplying both sides by 5. You're allowed. As long as you do it to both sides, you're good to go. What was the point of all this? F equals m change in v over change in t. This is this. They're the same thing. So what's the end result? The end result is that F, well, here, I'll write it the way that's here. Change in momentum over change in time is the force. However much your momentum changes over time is the force that's applied. So long, this is just another way of writing Newton's second law. Like it's another way of kind of parsing it out. And yeah, it's nice. Or if you really, another way, if you just rearrange this, your change in momentum will be a force applied over some time. If you apply a force, you're going to get faster or slower. Momentum is based upon how fast you're going. That's a part of it. It has velocity in it. If you apply a force, my momentum is going to either go up or down because you're either making it go faster or slower, depending on which way. Either way, you're changing your momentum. This slide is the exact same thing, just a little prettier. I write it out because if I show you all this, it looks like a lot. Remember, any complex process is just a bunch of small things strung together. So, great. Change it, and this is the slide that gives us the equation all nice and organized. There's the derivation, all that jazz. Impulse has a letter J. Why? No idea. I have no idea why they chose J, but they did. J just represents the change in momentum. And I don't know why it gets its own variable. It's just a change in a variable, but whatever. It gets its own letter. And like we just showed last time, the change in momentum equals force times change in time. If you have a force and you have a change in time, you can find the change in momentum. Or if you want, you can find the force by doing the change in momentum over change in time. This is just Newton's second law written another way. Not a big deal. It's another way of doing problems. But mention it because it's a thing. And now we're going to kind of look at this. We're going to look at this equation and apply it to a situation and make more sense of it. When it's all variables, it can be kind of tricky to understand what the heck's going on. All right, so we're just going to look at each of these variables now. Just to kind of show you what I mean. We're going to give a scenario, and we're going to look at the change of velocity, we're going to look at the change in the time, and then we're going to put it all together to find how the force is affected. So, if you get in a car crash, in which case will your face experience a greater change in velocity? Is it if your face hits the steering wheel? Is it if your face hits the airbag? Or it doesn't matter, your change in velocity is going to be the same no matter what your face hits. Give it a go. Again, chat with the people around you. There is only one right answer. Yeah. There's another energy PowerPoint. Okay. Yeah. Yeah, I took the two energy PowerPoints and we slammed them together.
Okay, I just thought I was crazy.
No.
Very confused.
No, I need to delete that one.
Okay, thank you.
I condensed them because there was no reason.
Okay, and I saw like some of the slides like overlapping, but I was like, how did I miss like
No, that's a good point. I'll fix that.
Thank you.
Yeah. All right, give you 20 more seconds. Go with your gut. Whatever your gut is, make sure the logic makes sense, all that jazz. All right, 5, 4, 3, 2, 1. All right, so how are we going to answer this? We're going to make up numbers. Okay, how fast are you going before the car crash? Give me a number. 60. Meters per second? Sure, let's do miles per hour. Why not? But we hate that. 27 meters per second. Great, 60 miles per hour. All right, great. That's my initial velocity. How fast are we going at the end? 0. All right, so my change in velocity is final minus initial. It's going to equal 0 minus 27. It's negative 27. Did I ever ask you what slowed you down? No. To answer this question, what's the change in velocity? Who cares what stops you? I mean, so this is what are you solving for? You're not solving for force. You're not solving for time. It's just asking how does your velocity change? I don't care what stops you. You went from 27 to 0. Either way that happened. Now in a complete, let's see how this went. Yeah, no one's going to like that, right? Now, there is something different about hitting the steering wheel, but it's not your change in velocity. You still went from 27 to 0 in either case. Now, someone asked a good question in the middle of this, which is a complete tangent, and I just want to mention it. So if you go to the Files tab, I know this is technically my studio class, but it's the same thing. If you go in week 7, there's like this potential energy and conservation of energy. Pretend like it doesn't exist. I'm just going to delete it from that class. I took both the weeks for energy. So it says week 6 is energy and week 7 is energy. And I took those PowerPoints and I made it one PowerPoint. So if you look at these PowerPoints, you're like, what the heck? We never did week 8 stuff, or whatever week it's supposed to be. Week 7, I'll delete that one. I smashed them together and I just didn't communicate that well. So yeah, anywho. So we're done with energy. There's just one PowerPoint for all of energy. One PowerPoint for all of energy. And there's going to be one PowerPoint for all of momentum. So I wanted to make that mention because if someone has that question, probably many people do. And it's a good question. All right. If you get in a car crash, in which case will your face slow down over a greater time? So which will make your face slow down over a greater time? Will it be if your face hits the steering wheel? Will that be the greatest time? Will it be if your face hits an airbag, that's the greatest time? Or both if you slow down in the same amount of time? There's only one right answer. And a rephrasing of this is if you hit something, what's going to slow you down quicker? A hard thing or a soft thing, or do they both slow you down the same amount of time? Yeah, longer time is slow, yeah. Which longer amount of time means it's a slower process. All right, so you got 10 seconds. During which of these is your so we're saying your velocity is going to go from 27 to 0. Does that happen in the same amount of time for both cases, or does it happen for a bigger time for one of these? If so, which one? All right, so 5, 4, 3, 2, 1. I am so glad to hear that people are actually chatting again, though. It was too quiet. It was all of the classes. It's too quiet. Didn't like it. All right. Okay, again, so let's look at another example. If I run into a wall or I run into a bounce house, which one's going to slow me down quicker? Let's do the opposite because that one's maybe a little bit easier. The wall's going to slow you down quicker. So which one's going to slow you down quicker here? The steering wheel. Which one's going to slow you down slower? The airbag. That's the greater amount of time. The airbag's going to slow you down over a larger time. All right, why are we doing this? Let's put it all together. If you get in a car crash, in which case will your face experience a greater force? Remember, I just gave you all a new equation. It's new and not in its own way. So F equals change in momentum over change in time equals m times change in velocity over change in time. So now that we've looked at change in velocity, we've looked at change in time, how do the forces compare? Go for it. There's only one right answer. The mass of your face is constant in both scenarios. All right, 10 more seconds. And 5, 4, 3, 2, 1. All right, so we look at this equation. How did their change of velocities compare? Was one bigger than the other, or were they the same? They're the same, so the top is the same. But the bottom, the time changes. If you have a bigger time, you have less force. If you have a smaller time, you have a bigger force. And it matches what you want it to be. The steering wheel is less time. Less time means bigger force. You accelerate. It's a higher acceleration. Your change in velocity is the same, but it's happening in less time. More acceleration, more force. Again, this is just another way of looking at Newton's second law. F equals ma. It's just coming from that. You can see that here, m times a basically. So, there you go. But it's another way of looking at it. And what's the consequence of this? Again, I honestly could have mentioned all this in like forces. The egg drop challenge is like a classic. Like if you've never done this, it's a fun one to do. You can do it at any age. You're never too young or too well. You might be too young at some point. Like my 8-month-old is too young, but my 3-year-old also probably would have a hard time with this. Anywho, it's fun to do. You build a structure that you drop an egg from 2 stories, 3 stories, or you toss it straight upwards, and you want it to survive. An egg has a certain amount of force it can withstand without breaking. Like, that's true of anything. Your bones have a certain force they can withstand without breaking, all that jazz. You exceed that force, it's going to break. It's just going to happen. Fun fact, it doesn't depend upon the orientation of the egg. You can test this for yourself. I don't know. Okay, I did a very rough experiment with this. Again, it's one you can do at home if you want. You get 2 and then you put one sideways, a person. We're assuming that the airbag is completely stopping the person. Thankfully, you have other things stopping you, like a seatbelt, hopefully. If the steering wheel is the thing stopping your face, your entire body, that's not great. You have a seatbelt, there's friction in your seat, stuff like that. So these answers aren't actually accurate. The force that you experience in a car crash is not this high. But whatever. It's still a good problem. I like this problem because there's 3 ways you can solve it. There's 3 different ways you can solve it using 3 different things that we've talked about in this class. So, what's the right way to do it? The way that gets you the right answer. And all 3 ways do so. Try it. Yeah, think about how you'd solve this. And again, feel free to chat. So you always start problems the same way. We could have drawn a picture here if you want. Car moving, car not. You can do that too if you want. But, there's the givens. Mass is 75 kilograms. Initial velocity is 20. Final velocity is 0. My change in position is 1 centimeter, 0.01 meters. Solving for the average force. Something I do want to encourage you all when you're solving problems. Up to this point, we've been doing our givens, and then we've been writing what we're solving for. As you get better at physics, something I encourage you to do is actually do step 2 first. What am I solving for? And then write down your givens. I've been doing it in the order of givens and missing because sometimes figuring out the givens helps you figure out what you're missing. But the reality is most things in life, you actually start with what do I need to figure out, and then you figure out what you have and stuff like that. So it's kind of the next step in becoming better at this is actually start with what am I even solving for? And that helps you identify the givens. So, all right. There's 3 ways to solve this. Go ahead and tell me what equations might let me solve this. That'll help me figure out. Our goal as a class is to come up with all 3 ways. We could do F equals change in P over change in T. That one has F in it. And then we look at this and we say delta V over delta T. Now to do this, I have M. I have my change in velocity. I do need to find my change in time. How could I find that change in time? How could I find the time of the collision? Kinematics. It still works, right? It's never gone anywhere. The equation that you all can use for kinematics is this one will immediately get you time. Again, there's many ways you could do it with kinematics. So that's just one of the kinematics equations. How do you choose the right kinematic equation? What do you need? What do you have? Choose the one that has those things. I have my change in x. So to clarify, xt minus x naught is the change in x. That's the same thing. So I'll move that over to the side. Great. That's one way to do it. There's 2 more ways. What are some other ideas? Basically, just let me know what other equations have force in it. There's not that many of them. F equals ma. Which, again, is kind of this equation in some ways. But instead of finding time, we look at this and say, oh, I've got mass. I need acceleration. How could I find acceleration? Kinematics. There's Vf squared equals V naught squared plus 2a delta x. You have Vf, you have V naught, you have delta x. You can solve for a. Great, that works. All right. There's one more equation that has force in it. What's the last equation in the formula sheet with force in it? It is work. You can do work. Work equals force times delta x times cosine theta. We know delta x. Cosine theta, it's going to be 180 degrees because you're moving to the right, and the force will be to the left. Then the question comes, work. Oh man, how am I going to find the work done? You'll tell me, what equation has work? Like, what's the classic way of solving? What's the other way of finding work? It's another equation that has a W in it. Sum of energy initial plus work equals sum of energy final. You could solve this with energy. What energy do I start with? Kinetic. What energy do I end with? None. So, let's see. I'll fit this in here. Which of these is the right way to solve this problem? All of them. Like, pick your favorite. None of them are better than the others. At the end of the day, you'll find that if you rearrange these, you're doing the same math. Just in different, it just looks different. Like, maybe the order that you're doing it is different. So this one, we start with kinetic energy 1/2 mv initial squared plus work equals 0. There's no potential. Well, we'll say the ground is 0. You're not going above. You don't start above or below ground. You do not end above or below ground. So there's no potential. There's no springs. You can find the work, plug it in. Again, it all ends up being the same thing. Which one am I going to use? I'm just going to do the top one because it's the new thing. So I'll do that. But all of them work. They all get you the exact same answer. So that's why I like this problem. Even though the final answers are a little bit nonsense and it'd actually be a little bit tricky to calculate the force of the head on it. Like, I would use the mass of the person's head instead of the mass of the whole body. The dashboard is not the only thing slowing down the head, so whatever. It's a little tricky to make this problem reasonable, but it's still worthwhile in its own way. Okay, so yeah, let's find our time. So delta x is going to equal VF plus V naught over 2 times time. So time is going to equal 2 times delta x divided by VF plus V naught. That's going to be 2 times 0.01 divided by 27 plus 0. That's a number, and it's a really small number, which is what you expect. I mean, you were going 60 miles, well, you're going 45-ish miles per hour, and your entire body got stopped by the steering wheel. Yeah, it's going to happen really quickly. Yeah, that's the 60 miles per hour, which is nonsense. There you go, 20. Yeah. That's a great question. I was stuck on my whole 27 meters per second is 60 miles per hour. All right, so 0.001 seconds. Happens really quickly. Makes sense. All right, and then another pin. Let's do blue. Then we just plug that up here. If you want the force, it's going to be 75 times 0 minus 20. Final minus initial, just because the final is a 0 doesn't... It's very, so we're going to get a negative here because we're assuming we're going to the right, and so the force will be to the left. And the answer that I give you all is a positive, but that's mainly because I just didn't tell you in this problem which way you're moving. If we assume we're moving to the right, you get this answer. And, it's a big force. Honestly, this problem, it'd be a little bit trickier. If someone was, running this fast and ran into a wall, that'd be kind of more so accurate to this force. Yeah, if you're going 20 meters per second and a wall stops you, yeah, because your body will... Obviously, the wall is not going to compress, but your body will. Your body's a little squishy. Your body will compress probably a centimeter. And yeah, if you run into a wall going 20 meters per second, you will die. I mean, that's what you expect, right? If you run into an airbag, you also probably aren't going to do too hot. There's a reason you have a seatbelt, and the airbag is not literally the only thing stopping your body. You need to spread out that force over an area and all that good stuff. Pressure and whatever. So great, there's that problem. Part B, I'm not going to solve because it's do the same problem but change delta x. Nothing exciting there. Okay. This problem has nothing to do with anything we just covered, but this is a relic from when I taught 2048 in the past. And I reminded you all there was a few questions on the test that a lot of people missed. This is just an additional practice of that. My Physics 1 for Engineers class also missed. So this has nothing to do with momentum, but still try the problem. Basically, this is just checking to make sure we know how to do this. So if I get this problem on the final. Draw the free body diagram for an object moving in the air, moving to the right. Do not ignore air resistance. The object is in the air. Doesn't say how it ended up there, but who cares? It's in the air, moving to the right. There is no rocket attached to it. There is no propeller attached to it. This is our third chance of redemption on this problem. All right. If you have like 30 more seconds, check with the people next to you. If you have different arrows, one of you's wrong or both of you's wrong. All right, so what's pushing or pulling it in the air? Y'all tell me. Air resistance. Which way is air resistance? Left. It's in the name. Air resistance resists motion. If you're going to the right, it goes to the left. It's always resisting. All right, what else? Gravity. And if you put anything extra, you added too much. This is it. So again, the most common mistake people make with this problem is they want it to be pushed. Just because something's moving doesn't mean it's being pushed. That's the idea here. It's in the air. It's no longer, yes, someone had to throw it or something, but we don't care what happened then. We care about when it's in the air, whatever. That's just a reminder on that. Fantastic. All right. And we're back to momentum again. All right. This is how we're going to solve every problem. This equation is the rest of the PowerPoint. Add up all your momentums that you start with equals all your momentums that you end with. That's all we're going to be doing for the next mini slides. It's super useful. Because, all you need is the mass and velocity of the objects. You don't care where they are. You don't care how they got that way. You just care that there's no extra forces acting on it, that there's, if net force is 0, meaning all the forces are internal. Things can push each other, but so like I'll give an example. When I say the net force is 0, so like one example of this problem that is interesting is an astronaut in space. Boop, boop, boop. There's my astronaut in space. Wow, he's floating. And he wants to move to the left. And he's holding a wrench. Whatever. There's, how awful is my wrench going to be? There it is. Wow, what a nice wrench. This is a terrible thing for an astronaut to do, but desperate times call for desperate measures. Great, he's floating in space. How can he move backwards? What could he do? Throw the wrench. Why does that work? If he throws the wrench, which way is he pushing the wrench? He's pushing the wrench to the right. But Newton's third law says for every force, there's an equal and opposite. So if he pushes the wrench to the right, the wrench is going to push him to the left. This seems silly, but this is how rockets work. Replace a wrench with hot gases. You push hot gas to the right, rocket gets pushed to the left. So we're going to see some problems like this. The net force in this picture is 0. They cancel each other out. So that's right, like there's still forces, but they all cancel each other out. So that's why I gave this example. F net in this picture is 0, which is just to kind of give that. So yeah, it explains how rockets work. It is a really interesting thing about space travel, where if you want to move in space, you have to shove stuff the other direction. If you're in space, let me rephrase that. If you want to change your velocity in space, if you're already moving, you'll keep moving forever and ever and ever and ever and ever. If you want to stop, you actually have to start shooting stuff in front of you. So like the fun example of this is for a rocket. If you want to get somewhere as fast as you can in space, you're going to fire your rockets behind you half the journey. When you get exactly halfway, you're going to turn your rocket around and then start firing the other direction. Otherwise, when you get to your destination, you'll fly right past it. By the time you get to your destination, you have to stop. You do not want the planet to be the thing that stops you. So yeah, in space, if you want to get somewhere as fast as you can, you spend half the journey accelerating and you spend the other half decelerating, which is not something you'd expect. You just think, oh, I'll just get there and stop. If you spent half the journey speeding up, you're going to need half the journey to slow down, unless you fired the rockets more or whatever. But this is one of the challenges of rockets. This is why they have to bring so much fuel. If you run out of fuel, you can't just start throwing wrenches. So whatever. Completely aside. All right. When to use conservation of momentum? If a collision or separation occurs. Two objects hitting each other and sticking together is the exact opposite of an object stuck together and separating. They're the same thing in reverse. So we're going to do problems like that. There's two types of collisions. Elastic, which they bounce off each other. There's very few elastic collisions out there because they have to bounce off each other perfectly. And for them to do that, always the example that gets used is billiard balls, pool balls. They're really rigid. They bounce off each other really nicely. Most objects don't bounce off each other nicely. A TA did give me another good example today. Atoms bounce off each other perfectly. That's another interesting example. But most objects don't. Inelastic is much easier to make. That's two objects hit each other and stick together. Or they can even kind of stick and then separate. We're not going to do any of those, but that actually does work. You can have objects that kind of get stuck together and then kind of separate, but we're not going to see any of those. Okay. Something I want to point out, I forgot to do on the last slide. I got two common things. These are vectors. What does that mean? You need to sum up the momentums in the x. Yeah, they're vectors. There is no escape. There is no shortcuts. I would love to be able to tell you all, nope, you don't have to deal with this. But then I'd be a liar. If you have things moving in a three-dimensional world, you got to work in all three dimensions. Now, I'm sparing you at least one of the dimensions, so that's kind, right? We're only working in a two-dimensional world. Could be worse. Could be the real world. And all its three-dimensional funness. If it was 3 dimensions, you would just have a third one. So, split everything into x and y. All the momentums in the x direction will equal all the momentums in the x direction at the end. All the momentums in the y direction in the beginning will equal all the momentums in the y direction at the end. You cannot just do all the momentums in the beginning and you have to split them up. You have to. If you do not do it, you will not get the right answer because the world just doesn't work that way. So, all right, great. There is two equations we have access to. We still have energy. Energy still exists. We're not going to actually do. I'm going to spare you all. There is one example where you have to use both, and I believe I'm going to spare you all from that one because it's really mathy and it doesn't add much value. Elastic collisions. There is problems I can give you with an elastic collision where you have to set up both of these equations, and then it's a system of equations, and it's very unpleasant. And I won't make you do that. It's not bad. It's just mathy. So whatever. They both still exist. Don't forget about that. Okay. Now we're going to practice building we'll just call this the beginning. I have two objects, M1 and M2, which each have their own velocity, V1 and V2. What is their total momentum? We're just practicing summing up momentums. That's all we're doing here. Only one right answer. Please talk to each other. If you don't know anyone around you, meet someone new.